Welcome back to Calculus 2. Today we're going to look at applications of first-order linear differential equations. The first application we're going to look at is motion with resistance. These problems are actually from a different textbook than ours, but they're similar to the ones we have in ours. So these problems are actually from Calculus Early Transcendental 7th edition by Stewart, very well-known book. Has a newer edition now, but I'm using an older edition. This is section 9.535 from that. So let's investigate this a little bit. So we're dropping an object that has mass m. We're not throwing it down, so it's dropped from rest. And if the air resistance is proportional to the speed of the object, which is reasonable in any medium, the faster you push something through, the harder you have to push. You know, like in water, if you're pushing something through water, the faster it's going, the more resistance you're getting from the water. So if you assume that air resistance is proportional to speed, well, that's just straight from algebra then. If V is proportional to the resistance, then the resistance equals a constant times V. If we set up S to be the distance the object falls after t seconds, then of course the derivative, the rate of change of distance, is velocity. And the acceleration is the derivative of velocity, or the second derivative of position or distance if you prefer. We know then that from Newton's second law that force equals mass times acceleration. So the downward force on the object is the force due to gravity minus the resistance, and then we know mass times acceleration equals the net force. Alright, so we got three parts of this problem. Problem 35. We want to solve the differential equation to find the formula for velocity. So we have a linear equation because we have a derivative of v. We have a v term. So if we put it in linear form, m dv dt plus CV equal mg. Divide out the m, dv dt plus c over m. Those are both constants because the mass isn't changing. Equals g. So then this is a linear equation. We already know the solution to that. You got to find the integrating factor, which is easy enough. Integrating factor, I don't really want to call it v of t now, so I'll call it w. W equals the integral, or e to the integral of c over m dt. Since that's just a constant, it's e to the c over m t. So then, our velocity function is 1 over that, so e to the negative c over m t times the integral of e to the c over m t times g. G is just a constant, so you can pull that out. G e to the negative c over m t. Integrate that. You'll just divide by m over c. You just divide by c over m. So you'll get m over c e to the c over m t minus, and we'll call this some other constant. Let's see, what do I want to call it? I'll call it A. And we do actually have an initial condition, so we can find A because we know the velocity at time 0 is 0 because we dropped it from rest. So v of 0 equals 0. So then, v of 0 equal g e to the 0 times m over c e to the 0 minus a equals 0. So you can divide off all of that. So that's m over c minus a equals 0. So a equals m over c. So then, our velocity function, just going to put this up here. Velocity function is g e to the negative c over m t times m over c e to the c over m t minus m over c. And since we got that, might as well pull that out as well. G e to the negative c over m t. Might as well say mg over c e to the c over mt minus 1. And honestly, I might as well just take this e to the negative c over mt into it, because multiply this times that, you just get e to the 0, which is 1. So this will just be mg over c times 1 minus e to the negative c over mt. That's probably the simplest version of it. So what is the limiting velocity? Well, that's just saying, what is this velocity going to approach as t goes to infinity? Because you might think, well, it might increase infinitely, but let's look at this. What is the limit for part B? What is the limit as t goes to infinity? Because the truth is, since the resistance increases, at some points the resisting force is going to equal the forward force, the accelerating force. And at that point, it's not going to go any faster. It's basically terminal velocity for falling. So, let's see here. Limit as t goes to infinity of v of t. The constant isn't going to be affected. What's going to happen to this? Well, let's see. Limit as t goes to infinity of 1 minus e to the negative c over m t. This is a negative exponent because both c and m are positive numbers. M, remember, is a mass. It is directly proportional, so c is some positive constant c. This is going to 0. This is going to 1. So, if that's the case, this is going then to mg over c times 1, or just mg over c. So this calculation, mg over c, is the limiting velocity. So if you're looking at a 300-gram object times acceleration due to gravity, you'd have to do unit conversions divided by the constant. Constant's based on the air resistance, and it's usually based on whatever medium you're in. So like in water, there's a different constant than in air. Find the distance the object has fallen after t seconds. Alright, well now that we got velocity, we need to find position. Let me give myself a little bit more room here. Distance. Well, velocity is this. Velocity is mg over c, 1 minus c over m, e to the negative c over m t. So integral of velocity will be position, so s of t would equal, see, integrate this, we still have that mg over c times t minus, integrate that, you get a plus m over c e to the negative c over m t, and then plus a constant. a new constant. So we'll call this b. I don't really think we have an initial height of the object. You could say, well, then, you could say this then, if s of 0 equal this, you could then say, well, s of 0 equal mg over c times 0 plus m over c plus b equal s sub 0 that's going to be m squared g over c squared plus b equal s sub 0. So b is s sub 0 minus m squared g over c squared. So then the position function would be mg over c times t plus m over c e to the negative c over m t. Should go lower. And then b is the initial minus m squared g over c squared. Honestly, this is probably fine for the original question, but I thought I would work it out in terms of whatever the original height was, because that would be the initial condition. That's all of this problem, but we're going to continue this in talking about 36. So 36 says if we ignore air resistance, we can conclude that heavier objects fall no faster than lighter objects. But if we take air resistance into account, our conclusion changes. So use the expression for the velocity of a falling object, which we've got right here, to find dVdm and show that heavier objects do fall faster than lighter ones. Alright. Let's do some erasing. So we want to find dVdm because we want to know if the velocity changes as the mass changes. Because that's what it's asking. If we have a larger object, is it going to fall faster than a lighter object? In a vacuum, they don't. A very famous experiment is when we first got into space, they actually photographed dropping like a feather and a really heavy object, and they fell at the same rate. Not so when there's air resistance. So let's see. dVdm. We've got an m in the exponent here, and we got an m right here. So we do have to do product rule. So derivative of this part in terms of m is g over c. 1 minus e to the negative c over m t. That g did not come out well. G over c. And then plus, leave the mg over c alone. Take derivative of this. Derivative of 1 is zip. Derivative of the inside. Let's see, derivative of the e part. Let's see, you're going to bring the derivative of the exponent down. So it's going to be plus e to the negative c over m t. I think we ought to be able to do some combinations here. I can pull out the g over c. That'll leave us with 1 minus e, negative c over m t, plus m, e to the negative c over m t. So how do we show that heavier objects do fall faster than lighter ones? Well, let's just consider as m gets larger. So let's look at the limit as m goes to infinity. Let's see, we got a constant here, g over c. Got this 1. Got g over c times 1 plus, let's see, m minus 1 times e to the negative c over m t. Now you might ask then, okay, well, what's happening? Well, as m goes to infinity, this is just going to e to the 0, which is 1, but this is going to infinity. So you're getting larger and larger increases in velocity. So certainly, yes, if you have an object with a higher mass, the velocity actually increases more quickly as well, because this is just telling you acceleration here. So yeah, it will accelerate more quickly. Now that doesn't mean that heavy objects won't have a terminal velocity. They will, because it's not like objects usually change their mass while they're accelerating. Not unless you get into very high speeds and you're talking about relativity and things like that. I don't even know if that's accurate. It's been a long time since I've done high-minded physics. So yeah, certainly a change in velocity increases as mass increases. So yes, heavier objects will fall faster than lighter ones. I think that's where we're going to end it for today. Next time we'll pick up with a couple more applications. One of the applications isn't really going to be of specifically linear equations. That'll be orthogonal trajectories. That's a neat little application. The other one will definitely be its mixture problems, and that's usually linear equations. Those are not usually just simply easily separable. You usually have to go through a little bit more work than that. So, have a great day.